Great to see you here again. This is a new video related to quality management and statistical process control. In this video, I will look deeper into the Taguchi loss function and its application. You remember that Taguchi was one of those gurus, and one of the main things that Taguchi introduced was its loss function. Let's have a look at the other things that Taguchi did related to quality. Now, he said most of the quality problems are basically the result of a poor process design. Basically, it means that it's important to deal with this, adjust the processes so that their design is improved and that the quality increases. Taguchi introduced three concepts related to quality. First of all, he looked at quality robustness, and what he calls a quality robust product is a product that can be produced uniformly and consistently in adverse manufacturing and environmental conditions. What he advocates here is to remove the effects of the conditions instead of removing the causes. So it's a different approach, and we know that in certain environments it may be more difficult to get the same quality results as in very well protected environments. So there are ways to deal with this. The second element that we really want to talk about in this presentation, in this video, is the Taguchi quality loss function. Now, what he says is that compared to the classical approach where the cost of a product is zero, as long as it's produced between the upper and the lower control limits. Now, Taguchi says, well, it's not really true. It's basically that the cost increases when the specifications move away from the target value. Basically, those incurred costs are all internal costs, and there are some costs due to loss of customer satisfaction. Although a product may still be compliant, may still be produced within specifications, the fact that we're moving away from the target means that we are not providing the product as we want. There is a loss of quality even when we are between those limits and between those borders. Another concept he introduced was target-oriented quality. And target-oriented quality is a philosophy of continuous improvement to bring the product exactly on target. So basically what we're going to do is find out what the difference between the target and the reality is, and we're going to improve the processes so that the target or that the outputs are closer or, in the best case, exactly on target. But let's have a look now at quality and variability in the Taguchi function. Now, the classical design is shown in this graph here. So when we look at the losses, as long as we're between the lower control limit and the upper control limit, around the design goal, we consider that the losses are zero. The moment we reach the lower control limit or the upper control limit, the losses increase. Basically, the product has no more value anymore. All the value is lost. Now, Taguchi considers losses even when the result is between those borders. And the cost increases, loss of the product, as a function of the distance to the target value, and is expressed by a quadratic function which says L is the loss, is d squared times c. D squared is the square of the distance to the target value. So if we are to the left or to the right, the sign doesn't play a role because we have a quadratic function, multiplied by the cost of the deviation at the specification limit. Now, what do we lose at the specification limit? Well, that's the value C. So the moment we reach LCL or UCL, that's the maximum loss that we have, and that's what we can, in fact, or that we have to determine. Now, we're going to apply this in an exercise, and there are different things that we have to do. First of all, we have to find the cost at the deviation of the deviation at that specification limit. So that's the first thing to do. Once we have that, we can write the Taguchi loss function, and then we can do a calculation with some real numbers. So let's have a look at our example here. we sell a food supplement which should per package contain at least 150 grams of magnesium taurate. It's a special product. You can find it on the websites when you Google it. And basically, that's the condition that we have. The acceptable tolerances have been set at 15 grams to the left or to the right. So it means that the upper control level is, or limit, is at 165 grams and the lower control limit at 135 grams. When the mixture is out of tolerance, the goods are returned and we have a cost of 15 euro. So basically, that's the information that we have. And now we want to know what would be the loss when the amount of magnesium taurate, T, is equal to 140 grams. So when we look at the function here, we see the lower control limit, 135, upper control limit, 165. The design goal is 150 grams, we call it X. And we have the function L is D squared minus C, and we express D as X minus T is the distance from the target. So X is the target value and T is the actual value that we measure. And C is the cost per unit deviation. Now, what can we say here? Well, when we are at the lowest control limit and the upper control limit, the cost here is in fact equal to the full 15 euro. So now we can do the calculation. So let's have a look at the result of this calculation. When we look at it, first of all, we have to determine the value of C, so the loss per unit. T is 135 grams or 165 grams. Then the loss is 15 euro. And this leads to the expression that L is 15 euro, is C times X minus T to the square, plus C times 150 minus 135. We had T here in this case on the lower control level to be 135 to the square. And then we find that the coefficient C is 15 divided 225. 225 is 15 to the square. So basically the coefficient C is 1/15. Now step 2, we will write the expression of the Taguchi loss function. And we can say that L is 150 minus T to the square divided by 15. And now we can calculate the loss when the amount of magnesium taurate in our mixture is 140 grams, which gives us, in fact, 150 minus T is 140. So 150 minus 140 is 10. 10 to the square is 100. We have to divide it by 15. So basically when we produce there per box, our loss is 6.67 euro. The Taguchi loss function is a very good indication to show what happens when we deviate too much from the central value. And it can give us an indication when we do quality improvements. So for example, we have typically, let's say the losses, we have typically 140 grams there, or on the other side of the border. So we can in fact estimate when we reduce that variability, the variability of the process, even being within the same upper and lower control limits, we have an idea how much savings we have. Because we can say when the old situation, we have 6.67 euro as a loss per box or per product. When we reduce let's say the variance of the product, we will see that the loss is lower. Basically, it gives us an indication how much we are saving when we are doing some quality-related projects. And when we do a project, we have to know how much the project will cost and how much will we save by doing the project. We will not invest in projects that will cost us more money than it will save us. Taguchi is a very important concept, and it gives you a clear understanding how important quality is and what losses we can have when quality, even between the upper and lower control limits, even between the target values that we've set, is very important. We can identify what this difference is and how to deal with it. So that was it for the Taguchi loss function. You're doing a great job. I hope you like this presentation. A little bit more calculations. Some people like it, some people don't like it. Anyway, in quality, we have some calculations to do anyway. So I'm looking forward to seeing you in our next video. Thank you and bye-bye.